This video is part of the series related with the book Statistical Modeling with R that I published in 2023 with Oxford University Press. Now I'm going to talk about GLMs that have a count response and the case when this count response has many zeros or too many zeros. I start as always with an exploratory data analysis, then do the frequentist fitting of a certain type of a mixture model, the zero inflated model. I'm going to explain that what it means in a second, and then proceed with a Bayesian fitting of another class of mixture models, the zero augmented models. This term will also be explained in a few seconds. As usual, the codes and data to run this analysis are on the website shown in the slide. So the excess of zeros is a frequent cause of overdispersion and the lack of fit of count GLMs. The excess of zeros refers to when the relative amount is a term that is relative to the amount predicted by the probability density function employed to model the response variable. That is, we have an excess of zero with respect to the amount predicted for the Poisson distribution with a given mean. That Poisson distribution with that certain mean predicts a certain amount of zeros. If we have many more than that, then we would have an excess of zeros. So mixture models, what they do is that they combine either a Poisson or a negative binomial distribution and a binomial distribution to model this count data with an excess of zeros. This is just one solution to this problem. There are two frameworks of mixture models that we are going to consider here. First is the zero inflated, in which the observed values of the response variables are a mixture of two latent classes. Latent means that non-observable variables. There are sampling zeros for which just by chance the response variable can be zeros, and structural zeros in which the response variable is set to be zero because of structural reasons. These are to be modeled with a binomial distribution. So the sampling zeros are going to be modeled with either the Poisson or the negative binomial distribution, and the structural zeros by the binomial distribution. The other class of mixture models are the zero augmented models. These zero augmented models, unlike the zero inflated that happen to be more used in environmental sciences and biology, the zero augmented are more used in social sciences and economy. Here we assume that all values of the response variable are observable, not latent, not resulting from latent variables, and that different processes determine the presences and other processes determine the absences. That is, different explanatory variables might determine the probability of presence, and other might determine the actual counts, given that the counts are greater than zero. So these two frameworks can be shown in equations, showing the two equations. So they result from zero inflated Poisson and zero inflated negative binomials. The zero inflated Poisson has two parameters, the mu for the Poisson distribution and p for the probability of excess of zeros, of having a structural zero. And the zero inflated negative binomial has this negative binomial distribution has two parameters, mu and phi, the dispersion parameter, and it also has the p, the probability of observing a structural zero. Let's explain just one of the two distributions, focusing on the Poisson distribution. And so here the probability of observing a zero is the zeros result from the structural zeros that occur with probability p, and y minus p is the probability of not observing a structural zero but observing a random zero. This is the probability of a sampling or random zero. And here are the values for all other variables, all other values of the response variable, given that they're greater than zero. In the case of the zero augmented Poisson, which is the only case of the two that I'm going to explain, the probability of observing a zero is occurs with the probability of p, and we use a truncated Poisson distribution. Here is the truncation of the Poisson distribution for all other variables of the response variable that are greater than zero. So in these mixture models, the count part uses a log-link function, and the excess of zero part uses a log-link function. So in a way, these are two intertwined GLMs put together to model this particular type of values of the response variable. So we might include explanatory variable in either part. They may or may not be the same explanatory variables in each of the part, the count part and the excess of zero part, and we can put no explanatory variables in these two parts, in these two GLMs that are intertwined together. So the exploratory data analysis refers to a data set in which we want to determine the effect of competition and precipitation on the breeding success, that is the number of bird fledge per nest of a bird species nesting on an island off the coast of California. So I import the data. Here we have the response variable. We see that at least we have 50% of zeros, which seems like a large amount. The breeding density around the nest, which is a measure of the competition. The larger the breeding density, the stronger the competition, and the precipitation for each of the years. So we have 52% of zeros. We also show the relationship between the response and the explanatory variables. There seems to be essentially no clear relationship between the response and the explanatory variables, and the explanatory variables are not strongly correlated with each other, so which means that we can include both in the analysis. So there we can use the cumulative distribution functions and the QQ plots to compare the probability distribution that could be used to model these response variables. That we are going to consider 4 probability distributions: the Poisson, the negative binomial, the zero inflated Poisson, and the zero inflated negative binomials. The Poisson and the negative binomial distributions are fitted as usual with the fit-dist command or the fit-dist plus package. See, we simply indicate the value of the response, the name of the response variable that is in this data frame, and the probability distribution that we want to fit. This is exactly what was done in the previous model. Now, for the zero inflated Poisson and the zero inflated negative binomial, we need to use another package, which is called GLMs, and this GLMs package requires that we provide initial estimates for the parameter of the zero inflated Poisson and the zero inflated negative binomial. The zero inflated Poisson distribution has a parameter mu. This is the value that we compute, the sampling average of the response variable that we compute as the starting value for this value, and this is simply a seemingly complicated way of estimating the proportion of zeros in this for the response variable. This happens to have the parameter, the name of nu, in this package, and this parameter name here as nu corresponds to the estimate of p, the probability of obtaining an excess of zeros. Regarding the zero inflated negative binomial, this distribution has 3 parameters: mu of y, the mean of the response variable, and phi, the dispersion parameter of the response variable, and p, the probability of obtaining an excess of zeros. So we now provide as a list the sampling average of the response variable as an estimate of its mean, sigma, which now corresponds to the value of the dispersion parameter of the negative binomial, and p. So this sampling value, an estimate of this sampling value of the response variable is this formula: is the sampling mean raised to the square divided by the difference between the variance and the mean, which is exactly what is indicated here. So having fitted the 4 distributions, we can now make the 2 plots: the cumulative distribution plot and the QQ plot. Here we have in dots the values. So here is the 52% of zeros that we observe. But right away we see that two of the distributions are pretty bad. The negative binomial and the Poisson distributions are not reasonable candidates for the to model this data. And whereas here in the QQ plots, it's pretty hard to see this differences in these plots. We can see that some distributions are obviously wrong, but it's not clear which is best because of this mass of points that are shown here that amount to roughly 50% of the values of the response variable. So as a way of discerning that, I calculated the AIC for the four distributions, and even for skeptical of the AIC like me, the zero inflated Poisson has a much lower value of the AIC than all other distributions, and very clearly is the winner here. So we are going to fit the zero inflated Poisson the zero inflated Poisson model using the package GLMs, and so we introduce the response variable and the explanatory variables as usual. And for the CI formula, we indicate that we are going to introduce explanatory variables in this part as well. We standardize the explanatory variables prior to the analysis, and we find here two parts, a two-part GLM, the conditional model and the zero inflation model. The conditional model is taking into account all values of the response variable, including the zeros, model for the Poisson distribution with a log link function, whereas the zero inflation part is the excess of zeros, and this is modeled with a binomial distribution and a log link function. Therefore, this conditional part includes parameter estimates in the estimated with a log link function, and this zero inflated part includes parameter estimates obtained with a log link function. What we observe here is that the explanatory variables were standardized prior to analysis. Therefore, we can compare the magnitude of the two coefficients regardless of the significance, and we see that more or less have the same importance for the conditional part, and likewise for the zero inflation part. We see that both coefficients, both response variables, happen to have a statistically significant effect on the zero inflation part, but only one, and marginally, happen to have a statistically significant effect for the conditional part. So we can also use the rule of 4 that we explained before for the zero inflated part that use a log link function, and we can use the other explanation of the exponent of the slope -1 to express this as the relative effect of changing one value of a numerical explanatory variable on the response variable, as it was explained in the other video of the chapter 10. So in order to assess the goodness of fit of the model to the data, we are going to use the package Broom mixed, because this is what is adequate to gather the input of a statistical model fitted with the package GLMs. It's very similar to the package Broom that we have used before. So we use the command augment to gather the basic input for the residual analysis. Here we have the deviance residuals, which are inadequate to assess the goodness of fit of this data, for which we are going to replace them with the Dunn-Smyth residuals that we obtain with the command simulate residuals that was from the package Dharma. So these residuals stored here are going to be converted into a normal distribution, which only happens when the model fits well, and then introduced to the the data frame that allow us to make the following plot. In the following plot, we have the residuals against the fitted values, the predicted values, the residuals against the explanatory variables, standardize each of them in plots C and D, and in plots A, B, A, C, and D, we observe essentially no pattern and no big difference in the variation of the residuals in relation with the values of the fitted, and either of the explanatory variables. And we also observe that these Dunn-Smyth residuals happen to have a normal distribution, and therefore the model has a pretty good fit to the data. We can compute with a little bit of effort the McFadden criterion, which is the percentage of the deviance explained. This is not obtained automatically with the package GLM so we essentially fit the model M6.null, which is an update of the model M6 without the explanatory variable for the conditional part and without the explanatory variable for the CI formula. Therefore, it's a model without explanatory variables, and so which allows us to compute the McFadden's deviance criterion. So, communicate the results. We can show them with the tidy, with the command tidy from the package Broom Mixed, and we obtain the intercept and slopes here for the conditional part that was fitted with a log-link function, and for the zero inflated part, these parameters were obtained with the logit-link function. We can also obtain the conditional curves with the package ggeffects, which show for the entire model the effect of each of the explanatory variables that I recall were standardized prior to the analysis. So I'm going to fit a zero augmented model for a different data set. This data set examines the effect of prey and leaf dry weights, soil moistures, and seasons on the spider abundance on some small plots in Hong Kong. So I started by importing the data set. I imported the data set, and in this data set, this is the response variables, and these are the explanatory variables. So we have 69% of zeros, which is a pretty large amount. Notice here that the third quartile of the response variable is 1, and the maximum value is 12, which is probably very different from the rest of the distribution of this response variable. So I standardized the numerical explanatory variables prior to the analysis, and we are going to consider a zero augmented model based on the type of sampling used by the authors of this paper. So please see the book for a further explanation in this regard. So again, we use the cumulative distribution function and the QQ plots to assess which is the best probability distributions to use to model this response variable, and we are going to consider again the Poisson, the negative binomial, the zero augmented Poisson, and the zero augmented negative binomial. So as usual, we use the fit dist command for the Poisson and the negative binomial distribution. This is the same that was used in the previous video of GLM of counts. Whereas for the zero augmented Poisson, we now use the CIP, zero augmented Poisson, as zero augmented negative binomial from the package GLMs. So here are the two distributions that we are most familiar with, the Poisson and the negative binomial with its dispersion parameter phi, and the zero augmented Poisson is similar to the Poisson distribution, but it has an additional parameter p, which is the probability of observing a zero. This is a truncated Poisson distribution. And this is the zero augmented negative binomial, in which the probability of observing a zero is p, and the truncated part of the distribution models the rest of the values that are greater than zero with a parameter mu and a dispersion parameter phi. So what we do is that we provide initial estimates for the parameters of this these distributions, and here is again the formula for the dispersion parameter of the negative binomial distribution. So after fitting the parameter values for these 4 distributions, we make the following plots, in which we observe again that there are some distributions this is the 69% of zeros, which are all here too. And so here we observe that certain distributions are pretty bad, such as the Poisson distribution, also here shown in red, whereas other distributions are, well, not obviously wrong, so it's not obvious. So I computed again the AIC for the all distributions, and although I'll use the zero augmented negative binomials, based on the AIC, it could be said that I could have used the negative binomial as well. So I examined the relationship between the response and the explanatory variables, but given that the response variable has 69% of zeros, I omitted these values from these plots, because otherwise all these lines would have been flattened to the bottom. So here the important thing is in the bottom row, in which in the vertical axis we have the response variable, and in the horizontal axis all the explanatory variables with different colors for the wet and dry season. So what we see here is that there seems to be a negative relationship between orthoptera and dry weight and the abundance of the spider, a different relationship between the dry weight of the terrestrial arthropods depending on the season. At least this is what we see here, and not much of a difference in the relationship between soil moisture and the spider abundance, or the log leaf and the dry weight and the spider abundance depending on the season. So there seems to be more or less the same relationship for this for the 2 seasons in this case, and a very different one here. So this is the motivation to say that the Draconarius will have a zero augmented negative binomial with these parameters, and this happens to be called hurdle negative binomial in the VRMS package that we use. So we are simply stating here that we are modeling adding explanatory variables to the count part and not to the zero part. So let's make some sense of this get prior output. So these priors are going to be defined in the log and the logit link scales, as said before. So the mean amounts to the partial effects of these to the effects of these explanatory variables and this interaction. And here is the intercept that is affecting the mean. Shape is the amounts to the shape parameter or phi for the binomial distribution, whereas HU or nu corresponds to the probability of observing a zero. So the default variable, the default prior, for all the parameters are flat or nearly flat. So what I'm going to do is I'm going to define different parameters for the zero inflated probability, the parameter HU or nu in Greek, as a Greek letter, and a gamma distribution for the shape parameter of the negative binomial. I'm going to make a plot of these implied priors and contrast them with the implied priors of the default priors provided by BRMS. So what we see here is that the implied prior is essentially flat for the zero inflation probability, whereas I am assuming that the most likely value is 0.5, and that extremely low values and extremely high values are very unlikely. Whereas for the shape of the binomial distribution, this is the implied shape in gray, and this is the shape implied by the prior I am defining. So I simply indicate that the family here is hurdle negative binomial. This is how this is indicated in the VRMS package. and so we are essentially indicated that we are entering parameter explanatory variables here and interactions in the count part, but not in the excess of zero part. We are asking as usual for 3 chains, the usual amount of warm-up and iterations, and these are simply extra parameters that modify the algorithm that was suggested to me once I tried a first fit without attaining convergence. So here we have the marginal posterior distribution for all the parameters. I'm going to explain this in a second. And so we have the shape parameter here of the negative binomial are the probability of observing a zero. So we have the marginal posterior distribution for all parameters. We have, let's start by noticing that the r hat values are all very close to 1, whereas the effective sample sizes tend to be pretty high with the exception of the shape parameter and the intercept. Okay, so let's notice here that season was a categorical explanatory variable that has 2 levels, dry and wet. So here, dry is in the intercept. So this is the differential of intercepts between the dry, the reference value, and wet, the other value. So here we have an interaction between the dry weight of arthropods and season. So this season wet corresponds to the slope for the reference value of season, which happens to be dry, and so this is the differential of slopes between the reference value and the other value. So this means that the slope for relating the dry weight of terrestrial arthropod in the wet season is 0.43 units higher than the reference value of 0.02. The reference value of 0.02 for this value. So we, again, as usual, we have the mean of the posterior distribution, the standard deviation, and the credible intervals for each of these parameters, which are the probability of that each of these parameters lies between these 2 limits of the credible intervals. We can examine the posterior distributions for each of the parameters. The parameters, some of them have asymmetrical shape, such as the shape parameter of the Poisson distribution of the negative binomial distributions, and also asymmetrical distribution for the intercept. But all in all, the 3 chains seem to have converged to a common stationary posterior distribution. I'm not showing the traces for each of the chains for all the parameters, but they are pretty good. You can at least believe me. Whereas for the correlation of the parameters, the degree of statistical independence indicated by the autocorrelation of the parameters for each of the chains, we see that for most of the parameters, but not all, most of the parameters seem to have a very large number of statistically independent values for each of the chains, with the possible exception of the intercept and the shape parameter of the Poisson of the negative binomial distribution. So what is to be done then? So one possibility is to refit the model having a larger number of iterations, or refit the model adding a thinning rate. Which here we set only to 1. So we probably, if we add the thin rate of 3 or 4 or 5, these autocorrelations for some of the parameters will certainly disappear in a second refitting of the model. In order to assess the goodness of fit of the data of the model, we compute the Dunn-Smyth residual from the posterior predictive distribution. This is done by first obtaining the posterior predictive distribution and then using the transpose of this posterior predictive distribution. This is required just because of the requirements of the command create dharma. We include the observed values and the fitted or predicted values by the model, and we include as true the integer response. This smooths the response, the Dunn-Smyth residuals here generated, which are then converted into a normal distribution with this command, and then we add all the necessary input, which are these Dunn-Smyth residuals, converted Dunn-Smyth residuals, the values of the explanatory variables, the fitted values, and the Pareto K coefficients that allow us to assess the importance of each value of each data point on the estimated parameters. We can also obtain the Bayesian R-square, which here is very modest or pretty low. The model explains about 16% of the variation of the response variable. This is often the case when we have mixture models. So here are the plots. And so first we see the residuals against the fitted values, the residuals against all the explanatory variables. So let's disregard the right-hand side of the A plot because there are hardly any data points. So the left-hand side seems to be a pretty decent fit. The same can be said for this second plot, although we, in fairness, we see a more or less triangular shape here. For this type of for the variation of the residuals against the values of the orthogonal dry weight. More or less the same can be said for the arthropods dry weight of in the plot of the residuals against the terrestrial arthropod dry weight. There is a more or less triangular shape, not suggesting a too good fit of the model to the data. The plots E and F both and C, E, and F are all pretty good, showing a random scatter of the points, whereas for the distribution of the Dunn-Smyth residuals, they do indeed have a normal distribution. So the Pareto K coefficients show us that there are 4 points that are only in the good range, whereas all the rest of the points, roughly 250 or so, are in the very good range. So the model has a mediocre fit to the data. One can compute with some effort, please see the book for details, the overdispersion index for this type of models. And the overdispersion index, the median value of the overdispersion index is 1.42, suggesting that the model has not accounted for the variation. The fitted model has not appropriately accounted for the variation of the values of the response variable. So here I also compute the credible interval for the overdispersion index, which is between 1.36 and 1.77. 1.36 means that there is a 36% more variation than the one modeled correctly by the fitted GLM. So some output to be communicated for this GLM that has a mediocre fit of the data. We can compute the mean of the posterior distributions for most of the important parameters, and the 95% credible intervals in thin blue lines, and the 50% credible intervals with the thick blue lines, and also the shapes of the posterior distributions for each of the parameters. The shapes are pretty asymmetric for some of these parameters. Some of them are showing that some iterations are actually pretty far. Some of the fitted values are pretty far from the rest of the distributions for the probabilities of turning a zero from the intercept of the model, that are 2, and also for the shape, which are 3 of the parameters that did not have an extraordinarily good posterior distribution. So all in all, this model could be refitted by adding extra values or by extra explanatory variables or interactions, and by changing some of the attributes of the coefficients in order to improve the quality of the posterior distributions here obtained. So this video has explained how to fit a GLM
of a count variable when there are many zeros, with the exploratory data analysis for each of the two data sets, the frequency fitting for the zero inflated model, and the Bayesian fitting for the zero augmented model. Needless to say, one can fit a Bayesian model for the zero inflated model. Both Poisson are negative and nominal, and one can fit frequentist zero augmented Poisson or zero augmented model. You just need to take a look on the help of the GLM package for the frequentist models and the BRMS package for the Bayesian model. I hope you found this model interesting, and I see you soon in a coming model of this series. Thank you for your attention.